All stations, this is Opscon ETR reports main engine cut off. The flight is nominal.
This is spacecraft. Front RF disable.
The time is 3:48 a.m., December 7, 1968. The place is Operations Control at the Goddard Space Flight Center, National Aeronautics and Space Administration. A few minutes ago, an Atlas Centaur lofted this nation's heaviest and most complex scientific satellite to date, NASA's Orbiting Astronomical Observatory, known as OAO.
Two booms! Booms are deployed. The fuse are out! This is the OTD. We have boom erection. We're firing gas 4-8. Okay, we have
Success for OAO is important. Its mission is intimately concerned with many of man's oldest questions about the universe. The progress achieved came about by building steadily on the individual successes of the past decade. More importantly, this success offers continued promise for the future. When OAO's voice was turned on, experiments designed and built by the University of Wisconsin and Smithsonian Astrophysical Observatory provided astronomers their first sustained, unmuddied look at the ultraviolet, X-ray, and infrared emissions of the stars. Some say this one mission may increase man's knowledge of astronomy as much as Galileo did with his first telescope 360 years ago. His discoveries provided a base for all the knowledge of the moon through centuries of observation with telescopes. The progress of science accelerated with the advent of space flight. The Rangers brought the moon 1,000 times closer than the best Earth-based instruments. And the success of these gave promise of the magnificent results from Lunar Orbiter and Surveyor, which followed. These automated spacecraft gave man impressive aerial and surface reconnaissance of the moon and provided a technological base that gave assurance for the Apollo missions. The early NASA milestones in space were largely concerned with discovery and rudimentary mapping of Earth's environment. To the uninitiated, the numerous spacecraft, the Explorers, the Pioneers, and the Vanguards may have seemed confusing. Yet, in spite of scores of successful missions to date, we are just beginning to understand the phenomena near Earth. But what we have learned is of significance.
We now know that some of the most fundamental phenomena in nature are occurring on a scale and magnitude that cannot, under any circumstances, be reproduced on Earth. Therefore, we must go directly into space. These processes are likely to reveal to us in the future important points and ideas regarding the origin of the elements, the stars, our solar system, and even the conditions for the establishment of life on Earth. For example, let's take a look at the situation near the sun and extending outward into the interplanetary medium. We now know that hot gases flow at supersonic velocity outward from the sun continuously in all directions, extending far beyond the orbit of Earth. In addition, there are occasional explosive processes occurring on the sun. For example, giant solar flares, which not only produce large outbursts of ultraviolet radiation, X-rays, but also high-energy particles which find their way along magnetic field lines outward past the orbit of Earth and extending finally into the interstellar medium. It's very interesting to note, at this moment, United States space probes, such as the Pioneers, the Ogos, and the Explorers, are distributed throughout the inner solar system to form a network providing simultaneous data vital for understanding the inner solar system and the near-Earth environment. In fact, we might imagine that this whole region forms a solar laboratory for the use of investigators. It is clear that the fields of physics and astronomy are now largely merged in an interdisciplinary effort. The enormous achievements of the 1960s have been largely due to a parallel effort of experiments in space and experiments and observations on the ground. As we all know in science, it is the momentum achieved from the past that establishes the base and the ability to move with confidence and assurance to greater achievements and discovery in the future.
The advancement of knowledge most often comes by the methodical unification of facts derived from increasingly refined experiments based on earlier findings. The way we have augmented our knowledge of the sun is an example. The first orbiting solar observatory made possible long-term observations of solar activity in the ultraviolet and X-ray regions of the spectrum. The OSOs have firmly established some of the mechanics of solar radiations that have a direct effect on the Earth's upper atmosphere. Other spacecraft, such as the orbiting geophysical observatory, have been designed to establish the detailed patterns and correlations between these solar radiations and the state of the Earth's environment. On these spacecraft, many types of measurements are made by separate experiments and correlated with each other. The information is further enhanced and interpreted by ground observations or from aircraft, balloons, and sounding rockets. In this respect, man's present knowledge about space will take on even greater meaning as a bridge to deeper understanding. In the future, we will build on the base of knowledge given by earlier spacecraft. Spacecraft will be flown in Earth orbit with instrumentation designed to provide an understanding of the structure and mechanisms of the magnetosphere. Still other automated spacecraft are planned to make synoptic measurements of the solar environment away from the Earth's magnetosphere. They will study the interplanetary medium at widely separated points from the Earth to the distance of Earth orbit on the opposite side of the Sun. Planetary exploration itself has progressed dramatically because of America's ability to build interplanetary spacecraft. A milestone was reached in 1962 when we sent a spacecraft on a 180 million mile flight to the vicinity of Venus, man's first close contact with another planet. It also established our ability to perfect the complex spacecraft needed for exploration of our solar system. That success gave promise for even more spectacular accomplishments. One was a 1964 launch to Mars that took 22 television pictures. Here was information about the surface of Earth's neighboring planet, about which man had speculated for centuries. How far we've developed spacecraft technology is summarized by Mariner 69. It will carry to Mars the most advanced scientific payload of any planetary mission to date. Mariner 69 will provide improved imagery, sensing of the Martian surface temperatures, measurements of the planet's radius, and detailed information on the composition of its atmosphere and ionosphere. It will pave the way for an orbiter in 2 years for thermal and topographic mapping of the Martian surface. It will study the dynamic characteristics of Mars and observe its daily and seasonal variations from an orbiting spacecraft. In 1973, we will progress to a lander called Viking. In exploring the moon, we found the immense value of the combination of orbiter and lander missions, so this spacecraft teamwork will be applied again in the study of dynamic Mars. The lander mission will allow our first surface measurements of a planet's environment and composition and will initiate our search for life on Mars. Continued orbital coverage will complement the lander data and will provide new insight into the behavior of Mars. The overall plan for our planetary program calls for a balanced strategy. Each of the planets is unique and different in its own way, yet collectively they possess many characteristics applicable to Earth phenomena. Mercury, for example, smallest of the planets and nearest the Sun, offers an important opportunity to study planetary dynamics. Recent radar measurements of its rotational period have already dispelled long-held beliefs. Also, there is no confirmed explanation for Mercury's unusually high density. About Venus, there are many more questions than answers. Like Earth, Venus has a complex atmosphere with the presence of moisture and is similar to Earth in size and mass. Venus may well reveal the potential effects of Earth's mounting carbon dioxide air pollution problem. The planet Mars is like Earth in apparent seasonal changes. However, we have already learned that its atmosphere is thin and that the planet has very little moisture. Although the promise of intelligent life on Mars has diminished, it still offers the high hope of primitive life forms. Jupiter, largest and perhaps strangest of the planets, is more like the Sun than the other planets. It generates energy like our Sun and may represent a primordial form of planet whose chemical processes, once understood, may explain how life evolved on Earth. Jupiter will be one subject for 2 spacecraft missions in 1972 and 1973. Development is now underway for these pioneers, which will investigate a region never before entered by spacecraft. In the opposite direction toward the Sun, a dual planet mission past both Venus and Mercury is being planned for 1973. Valuable atmospheric data and television pictures will be taken at Venus, and the spacecraft will then continue toward Mercury to obtain our first close-up visual and thermal images of the Sun's tiny neighbor. For future missions, our attention is drawn still further out into the solar system. A particularly exciting opportunity exists for multiple planet missions in the 1976 to 1980 time period because of the relative positions of the planets at that time. A single spacecraft could use the gravitational fields of Jupiter, Saturn, Uranus, and Neptune for a continuous flyby. The last time this unique alignment occurred, Thomas Jefferson was President of the United States, and it will not occur again for 179 years.
We have learnt a lot about the moon and the planets in recent years. My generation of astronomers thought that there were things that they would never know, which is now knowledge amongst schoolboys. So far, the main contributions have come from unmanned, sophisticatedly instrumented vehicles that have gone out into space under remote control from the Earth. A lot of information has also come from ground-based instruments like our great telescope here, the 1,000-foot, the world's largest radio and radar telescope. The example of how the different investigations mix in together arose in a very nice way at the time in the fall of 1967, when the Soviets and we sent space probes to the vicinity of Venus. We now understand that indeed the surface of Venus is very hot, some 800 degrees Fahrenheit or more, and that the atmospheric pressure on Venus is more than 70 times as high as the atmospheric pressure on the Earth. That makes Venus a difficult planet to investigate, but not an uninteresting one. We have the question of why the Earth escaped a similar fate. Did it only narrowly miss becoming equally hot and inhospitable? We think that the answer probably is yes. On the moon also, we've had an interesting mix of information from different sources. There we've had the wonderful series of orbiter photographs, which we have some here, which have given us a very good indication of what the surface of the moon looks like. Optical appearance, and we really saw a tremendous amount of detail, that whatever could be seen. Then we had the surveyor photography and the surveyor detailed investigation of the surface, And we got a good idea of the nature of the soil, the kind of material that we're going to land on later. The Moon is the first body to be investigated in that detail. But the nearer planets will come under scrutiny too. We've had the beginning with the very nice Mariner shot to Mars, which has given us pictures such as this. There we saw that on Mars also, the ground is covered with craters, indicating there also, I think, that the dating goes back very far. And then there's the question of the origin of life. Did it originate on the Earth, or did it originate before or elsewhere? Was there ever life on any of the other planets? From a strictly utilitarian point of view, I'm not sure what the value of the answers would be. But values arise in the first place in men's minds. And these surely are some of the greatest questions to be asked. It is now a time that it may become possible to answer them.